Hi, folks. Welcome to part 3 of our rational function videos. So in this video, we're going to go ahead and go over example 2, and then I'll tell you about another extra credit opportunity. Okay? So for example 2, if we zoom out for a moment, you'll notice that it looks pretty much blank, except instead of giving you a function this time, I gave you a graph. Okay, I gave you a graph with some important characteristics, and we're going to try to reverse engineer the function. Okay, now I'm going to say, let's go ahead and start with our graph, and I'll zoom in pretty big. Okay, and let's take a look at some of the important characteristics on here. Now, one thing I notice is that I have a horizontal asymptote right here. And I'm going to go ahead and label this as horizontal asymptote of y equals -4. Okay. I also notice that I have a vertical asymptote. And this vertical asymptote has an equation of x equals 4. All right. I also have a discontinuity right here. I've got a hole. Let's choose a good color for this. Ooh, we don't really have any other ones. Let's go with a slightly different color of green. This hole is happening at x equals 2. Okay, so I found some discontinuity. I found a horizontal asymptote. And the last thing I should probably do is look for any x or y intercepts, okay? And so I notice that I've got an x-intercept here. All right, -1, 0. And I've got a y-intercept right here, 0, 1. Okay, so we ultimately want to write a function that has all of these characteristics. Okay, so I'm going to do this. I'm going to say, let's start with our discontinuity. Okay, kind of like we did before. We're going to start with our situation where we have a vertical asymptote. We're going to write that part into the equation. Then we're going to talk about what it looks like in the equation if we have a hole at a certain point. Okay. And because the discontinuities impact the domain, I'm going to suggest we actually go to the domain next and list all of those values. Okay. So let's start here for right now, and then we'll come back and see what we're going to do next. Okay. So I notice that there's a vertical asymptote at x equals 4. So let's go to our discontinuities. So a vertical asymptote at x equals 4 means the following. It means that x minus 4 is a factor in the denominator, right? Is a factor in the denominator. Now, I know that it's a factor in the denominator because I'm looking for something that makes the denominator 0, okay? And if I plug in 4 and I get 0, it means the factor was x minus 4, okay? We can almost think about it like we took this factor, and let me write this in pink here, x equals 4, and we just like moved the 4 to the left-hand side. X minus 4 equals 0, okay? So this, my friends, is our factor. All right, so I know I have one factor on the bottom, but let's see what it says about the hole again. So if we go back to our graph, we have a hole, oops, not there. We have a hole at x equals 2. So let's write out what that means, okay? A hole at x equals 2 means, all right, let's subtract the 2 to the other side. X minus 2 is a factor in it's not just in the denominator, it's in the numerator and the denominator. Let's cheat a little bit, just squeeze this right back in. There we go. All right, a whole at x equals 2 means x minus 2 is a factor in the numerator and the denominator. So what does that mean about our domain? It means that we can have all the numbers we want, but we can't have 4, and we cannot have 2, right? And if we look at our picture, we've got all of these values, but not 2. And then we've got all of these other values, but we're missing at x equals 2 and x equals 4, right? So our domain, we would say, is from negative infinity to 2, in union with 2 to 4, in union with 4 to infinity, okay? And then explain our reasoning, we say, because there are discontinuities at x equals 2 and 4, we cannot have those in our domain, okay? Because those are discontinuities, we cannot have those in our domain. All right, so let's stop for a moment, okay? Let's summarize what we had and start to write our function, okay? So inside this box, I'm going to write f of x equals. I know I'm working with a rational function, so I'm just going to go ahead and draw a whole big fraction line, okay? And I want to think about what I already know. I already know that I have an x minus 4 from the vertical asymptote on the bottom, okay? And let's see, this is the vertical asymptote. I also know that I have x minus 2 as a factor in the numerator and the denominator. And this one, I think we had colored this color, sort of other green, all right? But other green, because the factors are on the top and the bottom, means that we don't have a hole there, or we do have a hole there, rather. So that's what we know so far, okay? My next suggestion is to take a look at what is happening for the intercepts, okay? So let's start with the x-intercept, all right? So the x-intercept, oops, that's not the x-intercept. The x-intercept is -1, 0. I know that I want this to be -1, 0. That means when I set it equal to 0, I should get x equals -1. Like -1 will make my fraction equal to 0. That means that I have 0 equals x minus 2. Let's copy down what we have so far. X minus 4, x minus 2. That's the start to our function. But remember, we talked about how the only way to get 0 out of a fraction is if the numerator is 0, and that we don't actually care so much about that denominator. And so when we revisit that, we actually end up with 0 equals x minus 2. Now, this shows me that x equals 2 would be an x-intercept, but we know that's a hole, so that can't be true. So what we need then is another factor so that when I get that factor, set it equal to 0, I'll get x equals -1. So what is that factor? X plus 1. right? When I take x plus 1 and I set it equal to 0, I get x equals -1. That is my x-intercept, right? This means -1, 0 is the x-intercept. What do we use? Yellow. Okay. So what that means in my function is I can continue to add to it. In fact, in the numerator, I'm just going to put in that extra factor of x plus 1. Okay, so let's see, we did that, this. All right, now let's think about our end behavior here, right? We're actually going to save the y-intercept for last. We're going to go ahead and look at our end behavior. So our end behavior, it turns out that we have a horizontal asymptote of y equals -4. So let's write down what that means, okay? What does that mean for our equation? So since we have a horizontal asymptote of y equals -4, all right, the degrees of the numerator and denominator must be equal, okay? So since we have a horizontal asymptote of y equals -4, the degrees of the numerator and denominator must be equal to each other, okay? And one more thing must be true. The ratio of the leading coefficients should be -4, okay? So those two things, the degrees must be the same and the ratio of the leading coefficient should be -4. So let's go back and see, does our equation have the same degree on the top and the bottom, and is the ratio -4? Okay. All right, let's zoom back up. Look at our function that we've written so far. The degree of the numerator is 2, right? X times x is x squared, so degree 2. Degree of the bottom is also 2. X times x is x squared. And so since the degrees are the same, we know we've got our horizontal asymptote, okay? But we need that horizontal asymptote to be at -4, not at 1 like it currently is. The easiest way to do that, stick a -4 in the front. Now my leading coefficient of the numerator is -4, and the leading coefficient of the denominator is 1. And -4 divided by 1 will give me -4, okay? All right, we've got one last box to check, which is our y-intercept, okay? So our y-intercept, we want it to be 0, 1. We know from all the work we've been doing that a y-intercept is 0, a number, right? But in this case, we want that number to be 1. So let's just go ahead and plug 0 into our function and see if we get 1 out. Because if we do, we're good to go, okay? So f of 0 equals -4 times 0 plus 1 times 0 minus 2 over 0 minus 4 times 0 minus 2. All right, -4 times 1 times -2 That's going to be 8 over -4 times -2 is 8. All right, 8 divided by 8. Woo, that's 1. All right. That means that all the other answers we have are correct. All right, and if we zoom out so that it's all on one page for us, we can see that every single part of the graph and all of our equation pieces, they all line up, which is awesome. Okay. Now, I know these problems are complicated, and I wanted to make sure that we could sort of really focus on connecting all the dots here, okay? When you do your MyOpenMath assignment, it'll be a little bit more like one piece at a time, but when you get to the quiz for chapter 3, it's going to be something like this, where we're pulling all the pieces together, okay? Now, extra credit. Who doesn't love extra credit? I'm going to leave example 3 here as a bonus. Okay, so you can send me, you can make an appointment with me. All right, make an appointment with me once you've figured all of this out. And you're going to we could do it on Zoom, we could do it on person, we can figure out the details later, but you're basically going to show me how, if I have these x-intercepts, this y-intercept, these discontinuities, and no holes, how do I write the function? What does the graph look like? What's the domain? And what's the end behavior? Okay, so I'll leave this here for you to think about. You don't have to do it. It is 100% optional, but it is there if you want to really make sure that you understand all the different pieces here. Okay. All right, my friends, I'll see you in chapter 4.